Well, good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So today we're doing another video here, and this video is on what? What are we doing today? We are doing the covalent bonding worksheet number 6. That's right, folks. Before you watch this video, I want to make sure that you have watched the previous videos. That is covalent bonding worksheet number 5. That is covalent bonding worksheet number 4. That is covalent bonding worksheet number 3. That is covalent bonding worksheet number 2. And of course, covalent bonding worksheet number 1. You should be watching all of those videos prior to actually watching today's video of covalent bonding worksheet number 6. In addition to that, you should probably be watching this set of videos as well. And this set of videos is from the covalent bonding handout number 2. If you go to my playlist of honors chemistry number 6, that's the bonding collection. Watch bonding number 28, molecular geometry, and it will cover this table and more. That's critical. In addition to that, you should be going to my honors chemistry playlist number 6, the bonding collection, bonding number 11, Lewis dot structures. And I will go over in detail how to use the Lewis dot structures. So for today's video, you need to have watched the previous videos and you need yourself a periodic table. You need to understand how to determine valence electrons. Those are in the groups. That is group family 1, 2, 3, 4, 5, 6, 7, 8, and correspond to the following valence electrons of 1, 2, 3, 4, 5, 6, 7, and 8. In addition to that, you need to know that fluorine is the most electronegative element. And that is critical in determining the central atom in a Lewis dot structure, which is the element that is furthest from fluorine, but never hydrogen. All right, so I'm going to peel this away here and peel these rules away. We'll be referring back to these rules a number of different times. And then we're going to stack up these worksheets. Number 1, number 2, number 3, number 4, number 5, and then today's video, that is right, that is video number 6. Okay. All right. So here we go. Without further ado, what we're going to do is we are going to zoom in on this worksheet so that we can really get a zoomed in version. That's right. All right. So here we go. Zooming on in to our worksheet and let's zoom on in just a tad bit more. Yeah, I'm thinking this is what we're looking for. Just a tad bit more what we're looking for. I like how that rhymes. Very good. All right, so let's start with this first one here. This is PO4 3 minus, and that is a polyatomic ion. That polyatomic ion's name, you can either look that up or you should actually probably know this from the ionic compounds section, and this is called phosphate. So, phosphate. So what we're going to do is we're going to total up our electron pairs, and there is 1 phosphorus, and then the number of valence electrons in phosphorus is 5. That's right, 5. I'm going to multiply that by 5, and then there are 4 oxygens, and valence electrons in oxygen, well, that is 6. Okay, perfect. So 4 times 6. So what we have here is 1 times 5, that's 5, and then 4 times 6, that's 24. And then the other thing that's unusual, which is on this sheet of paper here, on this covalent bonding worksheet number 6, is this right here. See that 3 minus charge? That means that this is an anion, and what we're going to have to do is add 3 to that. I know that this is actually a kind of a confusing thing for most students, and so let me try to explain that. And that is the following. So electrons, what we are doing is we are counting up the number of valence electrons. And what charge do electrons have? Wait for it. Yes, you answered it correctly. That's right. They are negative. So electrons are negative in charge. And so if I have a three, if I am adding up electrons, this five is the total number of valence electrons in phosphorus. This is the total number of valence electrons in all four oxygens. And so if I have a 3 minus charge, I'm actually adding three more charges of negative. So that's why we're adding three instead of subtracting three. So what we're going to do is draw a line in the sand. We're going to add up these numbers here. That's 24 and 5. That is 29. 29, and then add the 3, that's 32. And with always, what do? What does the crazy hat chemist do? Well, he always divides by 2, and then you get 16 pair. Now, between oxygen and phosphorus, we need to find the least electronegative element. And so fluorine is the most electronegative element. So effectively, we're drawing a piece of a distance between the fluorine and the phosphorus, the fluorine and the oxygen. What is the longer distance? The phosphorus. And that's why phosphorus is the least electronegative. It goes in the middle, just like that. All right, fantastic. Then the next thing that we're going to do is we are going to draw the sign of the cross or a plus sign, however you want to view this, it really doesn't matter. But this is a 3 o'clock position, a 6 o'clock position, a 9 o'clock position, and a 12 o'clock position. And the other elements go in those positions, and that is an O, an O, O, and oh my, O. We're going to erase those dashed dotted lines because those really don't belong there ultimately in the end. And now what we are going to do is we are going to apply the rules to the Lewis dot structures. And these are the rules right here. These are the sequential steps for drawing Lewis dot structures. Number one, we summed up all the valence electrons. We added for negative charge, finally. Okay, then two, we're going to determine the central atom. That's the least electronegative, but it can never be hydrogen. We're going to place the additional atoms in the positions of a clock, like 3, 6, 9, and 12 o'clock. And now we're going to do 3A. That's place a pair of electrons between the central atom and the outside atoms. So that is done like such. That's one of those pair, two of those pair, three of those pair, four of those pair. Okay, fantastic. All right, so then the next rule is right here, and that next rule is if electron pairs remain, place pairs of electrons on the surrounding outside atoms. That's X as lone pairs or non-bonding electrons. So that's what we're going to do here. We've placed 1, 2, 3, 4 pairs of electrons. Now that's 4, then it's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and finally 16. I've used up all my 16 pairs. I don't have any more. Now we're going to verify the octet and duet rule as appropriate. Now the octet rule is going to apply. The duet rule does not apply today. Why does the duet rule not apply today? Because we do not have a hydrogen on this phosphate molecule. So I'm going to circle this. Are there 2, 4, 6, 8? That's the octet rule. That is correct. 2, 4, 6, 8. That is the octet rule. That is correct. 2, 4, 6, 8. That is the octet rule. That is correct. 2, 4, 6, 8. That is the octet rule. That is correct. And finally, that phosphorus. 2, 4, 6, 8. That is correct. I don't leave these circles here. That is, I actually do that in my head, but I need to label that so that you can see that. Now, the other critical thing that we need to do is that because this has a charge, whether it's positive or negative, what we're going to do is put brackets around this and then delineate that charge. That charge is a 3 minus. We're placing it in the same position that we had up there. All right, that's perfect. That is beautiful. You've done a fantastic job. Now what we need to do is come up with the molecular geometry or the molecular shape, and that is using the axe, A-X-E. The A is the central element. That is the phosphorus. That's A. The X's are the outside atoms that are attached to the central atom A, and that's 1, 2, 3, and 4. Are there any lone pairs on the central phosphorus? That's a no, so there's no E's. Now, what we're going to do is we're going to use our little table right here, and we're going to find out what AX4 represents. That is tetrahedral, tetrahedral. Perfecto. And then tetrahedral corresponds to a particular bond angle of 109.5. 109.5 degrees. Excellent. And now what we're going to do is we're going to figure out the molecular polarity, okay, based on the model. So what we need to do is do a model, okay, and here we go. Here is our model. Spinning that around so that you can hopefully see that here. This is the model of phosphate. There, this blue is representing that phosphorus. Okay, that's really a nitrogen, but the nitrogen can represent anything within the same group or family, and phosphorus is right underneath nitrogen. These red ones are representing the oxygen. They are all singly bonded. So you should see that this is a tetrahedral structure. If I were to place my fingers on all the outside atoms, are they the same? They are the same. So since they are the same, that means that this is a non-polar structure since it is symmetrical. So this is symmetrical and non-polar. By the way, I am giving you a really easy, simplistic definition of that polarity here with symmetry. All right. Perfecto. All right, now what we're going to do is we're going to do the next problem here. And that one is ClO3 minus. And that is a chlorine and an oxygen. That's not a carbon, iodine, and oxygen. So that's why I've labeled that there. The name of this is chlorate. This is chlorate. So we're going to look on our periodic table. We're going to find chlorine. Chlorine is right here underneath fluorine, and that has 7 valence electrons. There is 1 chlorine, and it has 7 valence electrons, so that would be 7. Then oxygens, there are 3 oxygens, and oxygen has how many valence electrons? Oxygen is right here, 6 valence electrons. That would be 18. And then we need to add 1 because there's this 1 minus charge right there. So what we're going to do is we are going to add 1 right there like that. So we're going to add up all these charges here, and that will give me 26 electrons there. As always, the crazy hat chemist divides by 2 so that he can get pairs. So we're looking for 13 pairs. That's our lucky number here today. We're going to find the least electronegative element is going to go in the middle, typically. All right, and so here we go. So I got a choice between oxygen and chlorine. So oxygen and chlorine. Now, this one is a very tough one, and most students are like, well, crazy hat, chemist, what's up with this? It looks like chlorine and oxygen are equal distant from each other. And you might think that that is the case, and maybe that is the case if you were to actually measure these out, okay? But oxygen is the second most electronegative element. So oxygen is not going to go in the middle, but the chlorine is going to go in the middle. So here we go, chlorine in the middle. Again, we always sign the cross or a plus sign, whatever works for you. Okay, and that's how we're going to place our other elements in the 3 o'clock position of this oxygen, the 6 o'clock position of this oxygen, the 9 o'clock position of this oxygen. All right, awesome. Now I'm going to erase those dash dotted lines. And now we're going to place our 13 pairs of electrons according to the rules of placement. And those rules are as follows. Bonding pair of electrons in the 3 o'clock position, bonding pair of electrons in the 6 o'clock position, bonding pair of electrons in the 9 o'clock position. That's 3 of my 13 pair. I have 10 more left. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've done those rules. Now, to verify this, I am placing the electrons according to the rules, right? I've placed a pair of electrons between the central atom A and the surrounding atoms X. The A is the chlorine in this case, the X are the oxygens in this case. If electron pairs remain, which they did, place a pair of electrons on the surrounding outside atoms X. Those are the oxygens, as lone pairs are non-bonding electrons. Now, if electron pairs remain, which in this particular case, there's one pair that remains, place the remaining pairs of electrons on the central atom A, which is the chlorine in this case, as lone pairs or non-bonding electrons. These lone pairs of electrons on the central atom are designated as E. Okay, so that's critical here. So I'm going to place that lone pair of electrons here on that central atom. And like we did with the phosphate, we put brackets around it because it has a charge. I'm going to put brackets around this and a 1 minus charge. Awesome. You guys are doing a fantastic job. Hang on. Now, the next thing we're going to do is do the AXE, the axe-like structure. Okay. And the A is that central chlorine. So there's only one A all the time. The X's are the physical atoms attached to the central atom. There's 1, 2, and 3, and 3, 6, and 9 o'clock positions as the oxygens. So that is X3. Then there is a lone pair on the central atom, and that's this lone pair. This lone pair is the lone pair that's on the central atom, and that's designated as an E. So now I need to find this on my table. So I'm going to look at my table. I'm going to find AX3E. So AX3E, that's trigonal pyramidal and a bond angle of 107. So trigonal, pyramidal, and that's a bond angle of 107 degrees. Now I'm going to build the model. Here is the model. So that is, I need something that can handle these 4 domains. So I've used this nitrogen here to represent that chlorine. I know that the chlorine is most commonly in the model set that we have is typically a green one, but I actually need to be able to be bonding other things to it and 4 domains. So this little paddle right here represents the lone pair of electrons on a central atom. The red ones are the oxygens. So is this symmetrical or asymmetrical? So that is the question with regards to polarity. And so that is, if I touch all the attachments to the central atom, are they all the same or is there something different? Well, that paddle is different than these red things. So most certainly this is asymmetrical. And if it's asymmetrical, it is polar. Okay, just so that you understand the bond angles would be as follows. This is 107, this is 107, and this is 107. Okay, it's a domain structure of 4 domains, but you have a lone pair on the central atom, and this lone pair right here compresses the bond angles of all the other bonds. It should have been 109.5 because it's a tetrahedral arrangement of electron domains, but with this one electron domain being non-bonding, it compresses the bond angle. That's why you get 107 instead of 109.5. Right? That is that next one. Now, the next one, excuse me, is CO3 2 minus. This is carbonate. Awesome. Carbonate. So carbon, there is 1 carbon. And how many valence electrons in carbon? That would be 4. So I'm going to multiply this by 4. That will be 4. Oxygen, there are 3 of them. I'm going to multiply that by the number of valence electrons in oxygen, and that is 6. So that's 3 times 6, that's going to be 18. And then, of course, we are going to add this charge that is with the carbonate. That is a 2 minus. So we are going to add 2. And totally adding all this up, we get 24 electrons. And of course, the crazy hat always divides by 2, so you're going to get 12 pair. The least electronegative element goes in the middle. That's a choice between either the carbon or the oxygen. So what's further from the fluorine? Here's the fluorine. Is it oxygen or is it carbon? Well, the carbon is obviously farther away than the oxygen is from the fluorine. So carbon is king. Carbon goes in the middle. So I'm going to place the carbon right there like that. And then I'm going to place then I'm going to have the X marks the spot or the sign of the cross. Perfect. And the oxygens go around it like 1, 2, and 3 in the 3, 6, and 9 o'clock positions. I'm going to erase those dashed lines that were in pencil. That's just to assist me in that placement. Now what we're going to do is we're going to place these pairs of electrons as is appropriate. So here we go. First rule, bonding pairs of electrons between the central and the outside, central and the outside, central and the outside. I have used 3 of my 12 pair. Then it is 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used up all my electron pairs. All right. Now what we're going to do is we're going to circle. And is there an octet here? That's 2, 4, 6, 8. Most certainly there is. Circle here. Is there an octet? 2, 4, 6, 8. Most certainly. That's good. Circle here. That's 2, 4, 6, 8. That's an octet. That is fantastic. And circle that central carbon. 2, 4, 6. Oh my. Uh-oh. We have a problem. This central carbon is lacking an octet. So how do we deal with this? We've dealt with this before with some of the previous videos, but just to make sure. So do you see that there's this intersecting section here, right here that I've delineated here? Okay, in this intersecting section, that carbon in the center and this oxygen at the 3 o'clock position are sharing this pair of electrons. They both have ownership because they're sharing those pairs of electrons. So this oxygen on the 3 o'clock position has 8. That's 2, 4, 6, 8. This carbon is lacking an octet by 2 because it has 2, 4, 6. Carbon needs an octet. So what we're going to do is we're going to keep the electrons with this oxygen that are there, but bring them in and share them with the carbon, and that will be in this intersecting section. That is, these 2 electrons specifically are going to be moved, and then they are going to form now a double bond in between there. And you should see that within this circle here of this 3 o'clock position oxygen, we have 2, 4, 6, 8. We still have 8 electrons. In this carbon circle, we have 2, 4, 6, and 8. Now it's maintained an octet. So I'm going to erase all this here, and then you should see what you finally end up having. This is what you end up having. Now we're going to place this right here like this, these brackets with the charge, and that's a 2 minus. Now, there's one more thing that we need to add to this. And someone's going to say, well, crazy hat, why did you choose the 3 o'clock position instead of the 6 or 9 o'clock position to share those electrons from the oxygen to the carbon? And here is the answer to that. So we need to fold this sheet of paper over just a little bit here, and we're going to slide this on up. Okay, so I'm going to show you 2 other possibilities that are most common and actually correct as well. So what I have here is correct, and I am going to do 2 more that are correct as well. So another option I'm going to draw these double-headed arrows here. Is we have our central carbon, we have our oxygen, our oxygen, our oxygen in 3, 6, 9 o'clock positions. And we could have drawn the double bond here between the carbon and the 6 o'clock position, and that would have been fine. Consequently, you should have the 3 o'clock position have 3 sets of lone pairs. The 6 o'clock position have 2 sets of lone pairs because it has a double bond. And the 9 o'clock position have 3 sets of lone pairs. Of course, you still need the brackets and the 2 minus charge. Well, Crazy Hat, why did you choose that 6 o'clock position? I don't know. So could you have chosen the 9 o'clock position? That is correct as well. So I'm going to draw another set of double-headed arrows here. And we are going to have brackets here on this one as well. I'm going to place these atoms in the same orientation, same charge on the outside. And here I'm going to do a single bond, and here will be a double bond. When it's a double bonded oxygen, it will have 2 sets of lone pairs, so it has an octet. And then the single bonded oxygens will have 3 sets of lone pairs so that they have an octet. The octet is absolutely critical. So there are 3 possibilities for carbonate. What are these called? These are called resonance structures. Resonance structures. And you will learn this then in an upper level chemistry class or in your organic chemistry class. These are very critical. Okay. Now, it doesn't matter which of these structures you look at, you're going to still get the same X. So the central element in all 3 of these resonance structures is the A. And I'm going to write that A down. In all 3 of these structures, there are 3 bonded oxygens attached to that central element. That's at X. Are there any lone pairs on the central carbon on any of these? The answer is no. So it's AX3. So what does this correspond to? So let's pull out our little data table. AX3 is trigonal planar with bond angles of 120. So trigonal planar at bond angles of 120. And so what we need to do is we need to build the model for this. So I'm going to show this model representing the first structure that I drew, and that is right here. You should see that that double bond is right here with that oxygen. This black is the carbon, and these reds are the oxygens. So this is in a trigonal planar structure. There, all the atoms are in the same plane. Okay, and this is representing that double bonded oxygen right here, and these are the 2 single bonded oxygens. If we were to do it in the second structure, then I would just turn this like this. Okay, same structure. If I have this one here, I turn it like this. And that is this third structure that I have drawn. Same structure, actually. So the question is, of the atoms that I'm touching that are on the outside, are they the same or different? Well, they are the same. So that means that this is symmetrical. And of course, non-polar. Okay, now I do want to make one caveat. So if there is a chemistry professor, instructor looking out there, are these polar? Well, they are polar based on their charge. Anything that has a charge is polar in solution. However, the polarity that I am looking at for the purposes of this video are, is it polar based on the X structure? I'm not looking at polarity with charge. I'm looking at polar with regards to the geometry. And with regards to the geometry, it is non-polar for carbonate. Okay, just to make sure that we have that delineation on this. It's very important. Okay. All right, now you know a little bit more. These are called resonance structures. Any one of these 3 resonance structures will be perfectly satisfied for the purposes of what we're doing in this general chemistry class. When we get to my honors chemistry class, I will be asking you for all 3 of those. All right, so now let's move on. Let's unfold this and let's do our next problem here. Okay, we're still on the covalent bonding worksheet number 6. And here we go. Oh, a quick little advertisement from our sponsor. Our sponsor today is the Crazy Hat Chemist. And um, please like, subscribe, give me a thumbs up, throw out some comments. The like button is going out of control. Do you see that the like button is going exponential viral out there? So continue to give me the likes. I greatly appreciate it. And pass this on to your friends. They will learn some chemistry as well, too. This next one is NO2 minus, which is nitrite. It's nitrite, not nitrate. This also has a charge to it, and that's that 1 minus charge. So we're going to have to add that into our total number of electrons. So how many nitrogens are there? There's 1 nitrogen. How many valence electrons in nitrogen? 5. So 5. That's 1 times 5. That's 5. How many oxygens? That's 2. How many valence electrons in oxygen? 6. That's 6. That's 12. And then, of course, I've already highlighted it for you, but there's a 1 minus charge. So we're going to add 1 to that right there. So that would be 18 total electrons. And of course, we always divide by 2. That's 9 pair that we're going to be dealing with. The least electronegative element is the one that goes in the middle, but never hydrogen. The least electronegative is the furthest from fluorine. So I have a choice of either oxygen or nitrogen. Which one is it? Which one's farther from fluorine? It's the nitrogen. So that means that the nitrogen is going to go in the center, just like that. All right, fantastic. So now what we're going to do is we're going to draw an oxygen here in the, oh, that's right, folks. I forgot about that. In the sign of the cross or the plus sign, there's our 3 o'clock position oxygen. And here is our 6 o'clock position oxygen. Okay, perfect. All right, so let's erase those pencil marks so that we can do our bonding and lone pairs of electrons. So the first, we have 9 pairs of electrons. First rule is place bonding pairs of electrons between the central element and the outside element, central element and the outside element. I've done that. The next rule is to place lone pairs of electrons on the outside elements. That's a 1, 2, 3. So total number of electrons so far is total number of electron pairs. 1, 2, 3, 4, 5, 6, 7, 8. And then finally, the central atom, 9. All right, looking good. This does need brackets around it. And then the charge, that charge is a 1 minus. Okay, we're going to circle the atoms and look for the octet rule. And here we go. So this 6 o'clock, sorry, excuse me, 3 o'clock position oxygen has 2, 4, 6, 8. That's an octet. The 6 o'clock oxygen has 2, 4, 6, 8. That's an octet. This nitrogen has 2, 4, 6. Uh-oh, that is a problem. So again, just like what we did with the carbonate, I'm going to highlight this section right over here. It looks like kind of an eye right here. And what we're going to do is this oxygen in the 6 o'clock position has 8 electrons. We're going to maintain 8 electrons, but we are going to share this pair of electrons right here with that nitrogen as well, and that will form a double bond there. Perfect. Now this oxygen still maintains an octet at 2, 4, 6, 8. And this nitrogen now has an octet at 2, 4, 6, and 8. So I'm going to erase all these circles. And that is looking beautiful, a thing of beauty right there. And then someone's going to ask me, well, Crazy Hat, can you do the same thing that you did with the carbonate? The answer is absolutely yes, you can. And so let's show that. There is an alternate resonance structure for nitrite. And what does that look like? Well, I'll put the atoms in the same orientation, okay? And I'll put the brackets around it, just like what we had before, and the charge. instead of placing the double bond here on the 6 o'clock position, I'm going to place a double bond on the 3 o'clock position. Okay, that double bond will have two sets of lone pairs on that double bonded oxygen. On the single bonded oxygen, it will have three sets of lone pairs of electrons, and that nitrogen will still have the lone pair of electrons on it like that. There should be a double-headed arrow in between these two structures here. And again, what are these structures called? Resonance. Resonance structures. Those are very important. Okay, our next column is the ax, and we can use either of these two resonance structures to determine the ax. The nitrogen in the middle is Ra. The two oxygens on the outside in the 3 and 6 o'clock positions are the x's, and there's two of those. And then, of course, there is a lone pair of electrons on the central element, that is an E. So what does that yield for us? Well, we're looking at AX2E. AX2E, that is angular or bent with a bond angle of 105. So angular or bent. You don't have to write both of these, you just need one of them. The bond angle is 105. And then, is this polar or nonpolar? Well, we've got to build the model to figure that one out. And here is the model for nitrite. Okay, you should see that this nitrogen is the blue thing. The oxygens are the red things. This paddle right here is the lone pair of electrons on the central nitrogen. I don't have the lone pairs on the oxygens because I'm just looking at that central. This is the double bond here on one of the oxygen to nitrogen bonds, or you could flip that, and then you should see that that double bond is on the oxygen to nitrogen double bond, and this is a single bond. As I touch all the atoms or locations of things on the outside, so are they the same or different? Well, they're different. This lone pair is different than these oxygens. Doesn't matter if they're double bonded or single bonded. That's not material. Are they the same or different? They are different. So that means that this is asymmetrical. It means that this is polar. Party on. Party on. All right. So that's beautiful. You've done a fantastic job with that. Now I'm going to unfold this here. We have one more to do on this worksheet, and then we will actually be done with this worksheet. The next one here is BeI2. That's beryllium diiodide. So that 2 and that di go together because the prefix for 2 is di. All right. Beryllium has, there's one beryllium. How many valence electrons in beryllium? Well, we need our periodic table for that. That's right here. Beryllium is 2 valence electrons. 2 valence electrons. So 1 times 2 is 2. Iodine, there are 2 of them. And iodine is right down here. It is right underneath the bromine, underneath the chlorine, underneath the fluorine, which has 7 valence electrons for the entire halogen group. That's 7. And that's 2 times 7, that's 14. Is there any charge to this? No, there is not. So there's the only one on this sheet of paper which has no charge. So I'm going to add these up right here. That will be 16. And of course, Crazy Hat always divides by 2. So that will give me 8 pair. The least electronegative element goes in the middle, but never hydrogen. Well, we don't have a hydrogen, so we don't have to really worry about that, not at all. So it's either iodine or, wait. Let's see if we can fit it all on here. Distance between fluorine and iodine, or the distance between fluorine and beryllium. Well, the distance between fluorine and beryllium is most certainly longer. So the beryllium goes in the middle, of course. Beryllium in the middle. All right, and then the sign of the cross or a plus sign, that would go here like this. And then we're going to place the atoms in the 3 o'clock position and then in the 6 o'clock position. we're going to adjust that and get rid of all these like dashed dotted lines. Now we're going to place our electrons. Here we go. All right, so here we go. We're going to place our bonding electrons between the central and the outside. Central and the outside. That's 2 of my 8 pair. I have 6 remaining. So that's 1, 2. Now we're going to place electrons on the outside atoms. 1, 2, 3, 4, 5, 6, 7, and finally 8. All right, now we're going to circle these here. We've got circling this. That's 2, 4, 6, 8. That's an octet. That's fantastic. It's 2, 4, 6, 8. That's an octet. That's fantastic. And then the beryllium, that's 2, 4. Ooh, uh-oh. That's not an octet. So question is, we have done this on one of the other worksheets, and I just want to delineate this one more time. And this is this rule right here. Boron and beryllium can be electron deficient. That is less than an octet, and this is acceptable. In fact, that's what's happening here. So do not double bond a halogen. Okay, so we're going to erase this right here like this. And here we go. That is going to be acceptable. Okay, we're going to make an X. We're going to chop this with an X. So here we go. That beryllium is the A. The atoms attached to it are the iodines, and those are the X's, and there's 2 of those. Are there any lone pairs on the central atom? That is absolutely not. So now what we need to do is look at our table and look at the structure. It's AX2. AX2 right there, that's linear and bond angles of 180. So linear, bond angles of 180. And now we're going to build that model, and here is that model right there like that. That is the beryllium. These are the 2 iodines, and these are single bonds. And the question is, I'm going to touch the things on the outside. Are they the same or different? Well, they are the same. That is symmetrical. And that means nonpolar. I want to mention one other thing with this. Now, I have drawn it in this structure by, it looks like it's a 90-degree, and it doesn't look like it's linear, but it is most certainly linear. Even though your structure here in the Lewis dot structure, I've given you the concept of 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock. It just kind of helps you get it until you actually understand it. And as you're drawing the Lewis dot structure, then you can draw it in the correct orientation. So another correct way to draw this would be actually the beryllium, the iodine, and then we have this same like number of lone pairs of electrons, and now this is in that linear fashion. Notice that neither one of these structures had the brackets and the charge because this does not have the charge to it. All right, let's zoom on out and show this entire worksheet here. Okay, maybe not too much. Here we go. Here is the covalent bonding 6 worksheet. Okay, and so what do we have? We have phosphate. What do we have? We have chlorate. We have carbonate. We have nitrite. And we have beryllium diiodide. And the only thing that's not on here that is on the back of the sheet of paper are the resonance structures for both carbonate and nitrite. All right. I hope you are actually learning chemistry. I greatly appreciate you actually watching the entirety of this video, staying till the end. I appreciate you actually watching it through this end and watching me make and build all these models. I think it's really critical that you listen to the whole entire video with all the words. I think you will get much more out of it than if you just zoom through to look at just what the structures are that I have drawn. So hopefully that really helps. I really appreciate your time and comments, and please like, subscribe, and tell your friends. Thank you very much. Bye for now.